Prove that there are an infinite many prime numbers. Okay, this is quite a strange problem. We're going to use what's known by proof by contradiction. So what's going to be our objective? So our objective is going to assume, in fact, the opposite, that we have a finite list of prime numbers and show that this leads to a contradiction. So let's have a look at this more closely. So assume that there are, in fact, a finite list of prime numbers. So we'll list them. So the list will be P1, that'll be the first prime number, P2, the second prime number, P3, and P right up until a certain number. In a moment, I'll show you this with a specific example. So this is a finite list, it doesn't go on forevermore. Okay, if we now let n be the product of these prime numbers, so we do P1 times P2 times P3 times all these up to Pn, and then add 1, so this little secret is to add 1, then if we divide n by any of the original prime numbers, P1, P2, P1, P2, P3 up to our Pn, there will be a remainder of 1. Now let's just pause the proof here. We'll come back to the proof in a minute and look at a specific example. Okay, so what I'm about to write here in blue is not actually part of the proof, but it might help your understanding. So if we now consider the finite list of prime numbers, and in my finite list, I'm going to have the first 4 prime numbers. So all I'm going to assume is that I only have 4 prime numbers. Here they are, 2, 3, 5, and 7. So this is my finite list. And then if I take the product of those, so I do 2 times 3 times 5 times 7, and then add 1, I get the number 211. Now, what can we say about the number 211? Well, first of all, it's not divisible by any of these 4 numbers, these 4 prime numbers in my list, because it's always going to give a remainder of 1. Okay, so what can we say about 211? Well, it could be a prime number, which in fact it actually is in this case, and this prime number was not in my original list. Therefore, I've got sort of a contradiction here. This list is not finite. There's an extra number here, 211. Or it could be the composite of 2 or more numbers, of which at least one of them will be a prime number not in my original list. It can't be divisible by a prime number in the original list because they all have a remainder of 1. So there will be some other prime number which might divide into those which is not on the original list. Either these two things, both these two things actually lead to a contradiction that this list here is not actually finite. There are actually other numbers in the list. So, to go back to the proof, none of the prime numbers in the list are factors of n, as shown here. We'll leave a remainder of 1. Hence, n must be a prime number or divisible by a prime number not in the original list. Okay, because we know that because none of these actually went into this number. Therefore, contradicting that all prime numbers were in the list, are in the list P1, P2, P3 up to Pn. And therefore, we can therefore say that hence there are an infinite number of prime numbers, because we can write down any finite list and add 1, and this situation will still arise here. Okay, so just this part here at the bottom is the end of the proof. This is just sort of considering a specific example. Okay, so this has been a video to show you how to prove that there are an infinite number of prime numbers using the proof of by contradiction. I hope this helps you, and I thank you very much for watching.